So we will now turn to a classic application, classic example of classical mechanics, namely the two-body problem. We start with the general two-body problem, and then later on we will focus on a particular kind of force between the two bodies, namely the Kepler force. But let us first start with sort of the general setup. And the general setup is two bodies, two masses, m1 and m2. We have some reference frame in space, and with respect to that reference frame, the first body is at position r1, the second body is at position r2. And these two bodies, they exert forces on each other. So the second body exerts on the first body a force F12, and the first body exerts on the second body a force F21, and by Newton's law, action equals reaction, this force F21 must have the same magnitude but opposite direction of the force F12. So we have F21 is equal minus F12. And we will treat that problem in the Lagrange formalism. So the starting point is that we write down the Lagrange function in Cartesian coordinates. The Lagrange function depends on the positions and the velocities of the two bodies. So it's a function of r1, r2, r1 dot and r2 dot its kinetic energy minus potential energy. The kinetic energy is mass over 2 velocity squared of the first body plus the kinetic energy of the second body, that's mass 2 over 2, and then velocity of the second body squared. And then we have minus the potential. And we had seen earlier when we discussed Galilean invariance that if we require for the system, we require Galilean invariance, then the forces and hence also the potential may depend on the distance between the two bodies only. So we have a potential that depends on the distance, so the absolute value of the distance vector r1 minus r2. Yeah, so this form comes from Galilean invariance. This is the starting point and the basic setup for the two-body problem. And we'll treat that two-body problem in 5 steps. And let me outline these steps on the next page. In the first step, we will reduce the two-body problem to an effective one-body problem. That's the first step by which we simplify the problem before us. So we reduce the two-body to an effective one-body problem. At this point, it's a one-body problem in 3D. But we will actually succeed in simplifying that further, and we will reduce that to an effective problem in one dimension only. So this is the next simplification, that we reduce this problem to one dimension. In the next step, we will make use of energy conservation. So we will look at energy conservation and the consequences that that has for the solution of our problem. It will bring an even further simplification. Then we are ready to look at the solution. So we look at the general solution. And finally, we will discuss physically what that solution means and what it looks like. These are the basic steps in which we are going to proceed. As always, or as very often, it's a matter of finding suitable, convenient coordinates. So we will change coordinates. And a first change of coordinates will be from the positions R1 and R2 in our fixed reference frame in space. We will move to center of mass coordinates and relative coordinates. This means the following. Let us recall the two bodies, M1 and M2. Our reference frame in space with the original coordinates R1 and R2. Now, somewhere between the two bodies lies the center of mass of the system. This is the center of mass. And the center of mass has position capital R. Now the formula for the center of mass position, that is something that we had looked at before. That is, it's the weighted average of the positions of the two bodies, and the weight of each body corresponds to its share in the total mass. So it's M1 over the total mass, M1 plus M2 times R1, plus M2 divided by the total mass times R2. That's the center of mass. And then we can introduce the relative position of the two bodies. And this is a vector little r. This relative position little r, this is defined as R1 minus R2. That's the relative position. So what we are doing is that we change coordinates from the original R1 and R2. We go to center of mass position capital R and relative position little r. It's an alternative way of specifying the configuration of these two masses. And then we can express the Lagrange function as a function of these new coordinates. So we have the Lagrange function now as a function of relative position, relative velocity, center of mass position, and center of mass velocity. You obtain this Lagrange function simply by taking the original Lagrange function that we had on the previous page, and expressing the old coordinates in terms of the new coordinates. So you insert this transformation law. It's a time-independent coordinate transformation, so it's a rather straightforward substitution. And then you find the Lagrange function in terms of the new coordinates. It turns out this Lagrange function is the total mass over 2, where I have introduced a capital M for the total mass, m1 plus m2, times the velocity of the center of mass squared. So that looks like the kinetic energy, but now it's the kinetic energy of the entire system, or the kinetic energy of the center of mass. So when we can consider the system composed of two bodies now as a single system with total mass capital M, that moves with the velocity of the center of mass, and the associated kinetic energy, that would be this term m half times r dot squared, capital R dot squared. But then, of course, the system is not just a single body, there are two bodies, and they can also move relative to each other. So there is another contribution to the kinetic energy that comes from the relative movement of the two bodies. So there's a term proportional to little r dot squared, so the relative velocity squared, and the factor in front is mu over 2, where mu is defined as m1 times m2 divided by m1 plus m2. And this is the so-called reduced mass. And finally, we still have the potential term, which is u, and that was a function of the distance between the two bodies. Now the distance is simply the absolute value of the relative position little r. Now the new form of the Lagrangian, the starting point is this transformation law that I gave on the previous page that expresses the new coordinates in terms of the old coordinates. What we need in order to obtain the new form of the Lagrange function, we need the reverse. We need to express the original coordinates in terms of the new coordinates. So we have to invert these two equations and write R1 and R2 in terms of the new coordinates capital R and little r. Let me give you the results of this inversion. So the position R1 of the first mass, that's the position of the center of mass, plus, well, then we have to go some distance from the center of mass along the distance vector towards the mass number 1. And when you do the calculation, you find that this is just the ratio m2 over m1 plus m2, the total mass, times r. This gives you, when you invert the two equations, this gives you the position of the first mass. The position of the second mass is the position of the first mass minus the distance vector, little r. So you simply subtract from this expression above, you subtract little r, and you find that this is the position of the center of mass minus m1 over m1 plus m2 times little r. Is that fine with you? I mean, here I skipped some details, but this is a really, I think, a simple inversion of the two equations. You can also plug in these two equations in the left-hand side and verify that they are consistent. Now, as a consequence of that, we find the velocities. We can write the velocity of the first mass, r1 dot. This is capital R dot plus m2 over the total mass, but let me write for the total mass now the capital M, that's a bit simpler, times distance vector time derivative, and for the velocity of the second mass you find velocity of center of mass minus m1 over total mass times distance vector time derivative. Now we go back to the original form of the Lagrange function. Remember that as a function of the original coordinates, r1, r2, r1 dot, r2 dot, this was m1 over 2 and then r1 dot. But let's now replace r1 dot by the term that we have above, capital R dot plus m2 over total mass little r dot squared. And now that we express this immediately in terms of the new coordinates, actually what we obtain is the Lagrange function already in terms of the new coordinates. So little r dot, capital R and capital R dot. So there's the kinetic energy of the first mass. Then we have the kinetic energy of the second mass. That was the second mass over 2 times the velocity of the second mass. The velocity of the second mass we found was capital R dot minus m1 over capital M little r dot squared minus the potential energy, which is simply given as u of the distance between the two masses. All right, then we have to evaluate these squares. From the first bracket squared, you see we get an r dot squared. We get an m1 over 2 r dot squared. From the second bracket squared, we get an m2 over 2 capital R dot squared. So summing up these two, we get m1 plus m2, which is the total mass. So we get total mass over 2 capital R dot squared. That was one of the terms that we had encountered in the new form of the Lagrange. Right, then we have these mixed terms. So from the first bracket we get 2 times capital R dot scalar product with little r dot times m2 over total mass, and then multiplying this in front with m1 over 2. So we really have m1 times m2 divided by total mass times velocity of the center of mass, scalar product with relative velocity. That's a mixed term that we get from the first bracket squared. Now, from the kinetic energy of the second mass, the second bracket squared, we get exactly the same mixed term, but with the opposite sign, because we have a minus inside the bracket. So these mixed terms, they cancel each other out. And then finally, we have the remaining squares. So these are from the kinetic energy of the first mass, we have an m1 over 2, and then we have an m2 squared over total mass, and then we have an relative velocity squared. And from the kinetic energy of the second mass, we get also a term proportional to the relative velocity squared. So I can take this outside a bracket, and the factor in front is in that case m2 half times m1 squared over total mass squared. And I forgot the squared here. All right, and then the potential energy. Now, but what we have here is we can take, we have two terms that look very similar, only that in the first case we have m1 times m2 squared, and in the second case we have m2 times m1 squared. We can factor out an m1 times m2, and then we have inside a bracket we have m2 plus m1, which is the total mass, which cancels against one of the capital M's in the denominator. And what is left is 1/2 m1 m2 divided by capital M. And this is precisely what we defined as the reduced mass on the previous page. That's how you obtain the formula on the previous page. In these new coordinates, it's easy to see that the motion of the center of mass and the relative motion of the two bodies actually decouple from each other. To see that, let us copy the new form of the Lagrange function. In this new form of the Lagrange function, you see that the Lagrange function is the sum of two terms. There's one term, this one here, which depends only on center of mass coordinates or their velocities. So this is, you can view that as the Lagrange function L1 of the center of mass. And then you have terms that depend only on the relative coordinates and their time derivatives. So you can view that as a second contribution to the Lagrange function, which depends only on the relative positions and velocities of the two bodies. Now, the fact that you can write the Lagrange function for the entire system as the sum of two functions, one of which depends only on the center of mass degrees of freedom, and the other one depends only on the relative degrees of freedom, this implies that the equations of motion for the center of mass and for the relative degrees of freedom, they decouple. So this implies that the equations of motion for the center of mass coordinates and the relative coordinates, they decouple. So in other words, the position of the center of mass does not enter in any way in the equation of motion for the relative position of the two bodies, and vice versa. let's quickly see what we can say about the dynamics of the center of mass. That is actually very simple, because we immediately see that the Lagrange function that describes the center of mass motion, this L1, does not depend on the center of mass position. It doesn't depend on capital R. It only depends on the velocity, capital R dot. So the position of the center of mass is a cyclic coordinate. This immediately implies that the associated momentum is conserved, is a constant of the motion. So this implies that the center of mass momentum, capital P, which is defined as the partial of the Lagrange function with respect to velocity. Let me write it in vector notation in this way. This is when you do the differentiation, this is simply the total mass times the velocity of the center of mass, that this is constant of the motion. And this immediately implies a very simple equation of motion for the center of mass, and the general solution is a uniform motion. So the position of the center of mass as a function of time has the general form. It's the position at time 0 plus the velocity, capital V of the center of mass, times t, and this velocity is constant in time. The momentum is constant in time. They are proportional to each other via the total mass, so the velocity is also constant in time, and this is simply a uniform motion. The center of mass of a two-body system simply performs a uniform motion. It's a very simple dynamics. So all the interesting stuff is in the relative motion. So from here on we can really focus on the relative motion, which means the time dependence of the little r. That's where the interesting physics is. So we focus on the relative motion from here on, and the relative motion is governed by this second term in the Lagrange function, the L2, which depends on the relative coordinates only. So this L2 will determine the relative motion of the two bodies. So now we focus on the relative motion and the second part of the Lagrange function, which depends only on the relative coordinates and the relative velocities. And with this we have achieved our first goal, the first goal that I mentioned in the procedure, in the outline of our steps, namely that we've effectively reduced the problem to a one-body problem. If you look at the Lagrange function that we want to focus on now, this L2, and I omit the subscript now, which has the form reduced mass over 2 times relative velocity squared minus the potential energy. This is precisely the Lagrange function of a single body of mass mu moving in a central potential. So effectively, we have reduced our problem to a one-body problem. namely a single body moving in a central potential. So from now on, at least for a good while, we can forget that we are dealing with two bodies, so we can simply now focus on the problem of a single body moving in a central potential. A central potential, or a central force, that is a situation that we had already considered in the framework of Newtonian mechanics. And we had already looked at consequences when you have central forces. And one important consequence was that the angular momentum is conserved. So we can immediately take over these results from our discussion in Newtonian mechanics, that a central force implies conservation of angular momentum. Now, conservation of angular momentum, you remember, had two implications. One implication was that and that comes from the fact that the direction of the angular momentum, in particular the direction of the angular momentum, is conserved. That implies that the motion is effectively constrained to a two-dimensional plane. So you have the initial position and the initial velocity of the particle. They span a two-dimensional plane, and the body will never leave that two-dimensional plane. So that was the first consequence that we had discussed earlier of angular momentum conservation, that the motion is constrained to a two-dimensional plane. And the second consequence was the area law, and we'll come back to that on the next page. If motion is constrained to a two-dimensional plane, then we can change coordinates yet again. Let me sketch that plane here, that two-dimensional plane. And let's say that our body moves in that two-dimensional plane. One thing we can do is we can introduce cylindrical coordinates, and the way we do that is that we choose the z-axis of the cylindrical coordinates to be orthogonal to this two-dimensional plane in which the body moves. And in the two-dimensional plane, we introduce coordinates rho and phi, where rho is the distance to the origin in that two-dimensional plane, and phi is the angle with respect to the x-axis. So the idea here is that we go to cylindrical coordinates. The two-dimensional plane, as I said earlier, corresponds to z equal to 0. So we change the z-axis in such a way that the motion is in the plane where z is equal to 0. Now when we do that, we go from the relative position little r now to cylindrical coordinates. Then we have to again express the Lagrange function in terms of these new coordinates, in terms of the cylindrical coordinates. The transformation law between Cartesian and cylindrical coordinates is x is given by rho times cosine phi, y equals rho times sine phi, and z equals z. This is the transformation law. Now the kinetic energy had the form in the original Cartesian coordinates mu over 2 times relative velocity, so little r dot squared. now express x dot, y dot, and z dot in terms of the new coordinates, then you see that this becomes rho dot squared plus rho squared phi dot squared. And in principle, you also have a z dot squared. But since we chose the orientation of our coordinates in such a way that the motion is always constrained to the plane corresponding to z equal to 0, then z is always 0, z dot is always 0, and therefore the z dot squared, we don't have to carry the z dot squared because the problem is effectively two-dimensional and the z coordinate doesn't play a role. Yeah? So I close the bracket here, and as a reminder I write z and z dot are always 0. The potential energy that was a function of the distance between the two bodies, again, we know the distance between the two the distance vector is confined to that two-dimensional plane. So again, there is no z component to worry about, and the length of the vector r is simply, in cylindrical coordinates, that's simply our rho. So again, using the fact that z is 0, we have eliminated the third coordinate. This allows us to write now the Lagrange function in terms of the cylindrical coordinates. So in terms of rho, rho dot, phi, and phi dot. It's kinetic energy minus potential energy. So we just take the two terms that we have for the kinetic energy and the potential energy. We immediately see that this Lagrange function actually does not depend on phi. Phi is cyclic, which implies that the associated momentum is a constant of the motion. The associated momentum, that's the partial of the Lagrange function with respect to phi dot. This is mu times rho squared phi dot. And we had seen earlier that that is the z component of the angular momentum. When we had talked about angular momentum conservation in the context of Newtonian mechanics, we had discussed also about the area law, and we found that this is in fact the z component of angular momentum, which in our case, since the motion is constrained to that two-dimensional plane perpendicular to the z-axis, this equals the absolute value of the magnitude of the angular momentum vector. So this is actually equal to the absolute value of the angular momentum, which we also simply write as a little l. So this is a constant of the motion. And this constant magnitude of angular momentum, as we had discussed earlier, corresponds to the area law. The area law, just as a reminder, when you have here motion in a central potential around the center of the potential, then the area covered by the ray connecting the center of the potential with the body. The area covered in a certain time interval delta t is always the same. So when the body moves from here to here, in a certain time delta t, the ray connecting the body to the center of the potential covers a certain area, this green shaded area. If the body is here, and again after some time delta t, the ray covers that area, and these two areas are identical. The ray always, in a given time interval, always covers the same, a constant area. The area law in particular gives you immediately an expression in a differential equation for phi. And you have this this equation, mu times rho squared times phi dot equals this constant angular momentum L. You can solve that for phi dot, and then you have a differential equation of the form phi dot equals something. On the right hand side you have rho of t. So once you know the time dependence of rho, you can plug it in there, and then you have a differential equation for phi, and you can solve for phi of t. So our next task must be to find the solution for rho of t. To do that, we have to consider the equation of motion for rho. That equation for rho is also known as the radial equation. We obtain the equation of motion for rho in the usual manner from the Lagrange function. It's an Euler-Lagrange equation of the form d over dt of the partial of L with respect to rho dot. This must be equal the partial of L with respect to rho. When you consider the form of the Lagrange function, in particular the kinetic energy, you see that the partial of L with respect to rho dot, that's mu times rho dot, and the time derivative of that is mu times rho double dot. And on the right hand side, when you take the partial of L with respect to rho, then of course you get the partial derivative of the potential with respect to rho, but you also get the contribution from the kinetic energy, because in cylindrical coordinates the kinetic energy also had a dependence on rho. So you get two terms. The contribution from the kinetic energy has the form rho times mu times rho times phi dot squared, and the contribution from the potential is the partial of u with respect to rho. At this point you can exploit the area law that we had found on the previous page. You use the area law to express phi dot in terms of the conserved angular momentum, the reduced mass, and rho. Using that, you find mu rho double dot equals, and then you have, for the first term, you get L squared over mu times rho cube minus the partial of the potential with respect to rho. And this equation of motion inside the box that's the radial equation. It's the equation of motion for rho. And the interesting aspect of this equation is that it's not simply mass times acceleration is minus the gradient of the potential, but there's this extra term there. In this extra term, you can, so heuristically, you can regard that as an effect, as a centrifugal force. It's an extra acceleration that comes from the angular momentum, the finite angular momentum of the system. If the angular momentum is 0, so if L is equal to 0, this term does not contribute, but as soon as the body is moving around the center and has a finite angular momentum, L is different from 0, and then you will have that contribution. So let me write that in quotation marks. You can view that as a kind of centrifugal force. And this is now an equation of motion for a single degree of freedom, for the rho. So you've effectively, after changing coordinates twice, you've reduced the problem to an effectively one-dimensional problem. That was step 2 of our procedure that I had outlined at the beginning, reducing it to a one-dimensional problem. The next step in the procedure that I had outlined was to exploit the conservation of energy. Keep in mind that all the coordinate transformations that we had done were time independent. Note also that the Lagrange function does not depend explicitly on time. So the partial derivative of L with respect to time is equal to 0. And as we know from our general considerations, this implies that the Hamilton function actually equals the total mechanical energy and is a constant of the motion. So the Hamilton function under these circumstances is the total physical energy, so it's T plus U, kinetic plus potential energy, and is conserved, so it has a constant value E. That is the total energy, and remember we are considering here the relative part of the motion only, so not the motion of the center of mass. So it's the total energy of our relative motion. Now let's evaluate the Hamilton function. Let's insert for the kinetic energy and the potential energy the formulas that we had obtained earlier. The kinetic energy had two contributions. One was mu half rho dot squared. The other contribution was included a phi dot squared, which we express using the area law in terms of rho. So that's L squared over 2 mu rho squared. That's the kinetic part. And then we have the potential energy U of rho. Now, even though the second term in this expression, in this formula for the Hamilton function, the second term comes originally from the kinetic energy, it's a function that does not depend on velocities, but it depends on rho, depends on position. And therefore, what we will do is that rather than considering it as a part of the kinetic energy, we group it together with the potential and call that an effective potential as a function of rho. And then we have written in this way, we have for the Hamilton function, for the total energy, we have a form that we know from one-dimensional problems, where we have a kinetic term, which is the velocity squared, plus some potential which depends only on position. So this is, we will now treat this as a problem in one dimension with effective potential, U effective, as I had indicated here in blue. Now, the sum of kinetic and potential energy is this constant E. We can solve that for rho dot. So we can first write mu over 2 rho dot squared equals this constant E minus the effective potential as a function of rho. Or we solve it for rho dot. This is the square root of 2 over mu times E minus the effective potential of rho. And this is now a first order differential equation, which at least in principle, not always analytically, sometimes only numerically, but in one way or the other, we can solve for rho of t. So here we are back to the procedure that we had at the very beginning of the semester when we started out with one-dimensional problems as the very simplest examples. We considered problems exactly of that form. We used energy conservation in order to find the solution of our problem. Before we come to general form of the solution and the discussion of the solution, let's pause for a minute and take count of the degrees of freedom and the integration constants. As for the integration constants, what would you expect? We have two masses. Each mass performs a three-dimensional motion. So if we want to specify the initial state of our system, we would expect that we need 3 parameters to specify the position of the first mass, 3 parameters to specify the velocity of the first mass, makes 6 parameters for the first body, and then another 6 parameters for the second body. So we would expect that we need in total 12 parameters to specify the initial state of our two-body system. That should correspond to the total number of integration constants that we have in our general solution of the problem. So let's check whether this is indeed the case, or whether perhaps we have lost integration constants along the way. In our general solution, we have, first of all, we had separated the motion of the center of mass from the relative motion. The motion of the center of mass had the simple form of a uniform motion, r0 plus the constant velocity of the center of mass times t. In this general solution for the center of mass, there are already 6 integration constants, namely the components of r0 and v. Next, we had introduced cylindrical coordinates, and we had oriented our coordinate system in such a way that the motion is confined to the two-dimensional plane corresponding to z equals 0. So we had now the question is, how many parameters do we need to specify the orientation of the plane? To specify the orientation of a two-dimensional plane in a three-dimensional space, you need 2 parameters. Because you need, one way you can do that is that you specify the direction perpendicular to the plane. So you have to specify a vector perpendicular to the plane. The length of the vector is irrelevant, only the direction of the vector is relevant. And the direction of a three-dimensional vector is specified by 2 parameters. What we did was that we oriented the cylindrical coordinates such that z is equal to 0. Now in this choice, we have two parameters that specify the orientation of the plane. Then we had our radial equation. Then we had to reduce that to a one-dimensional problem. We had our radial equation. So the radial equation followed from energy conservation, and from that form mu half rho dot squared, that must be equal to the constant energy minus this effective potential, which depends on, amongst others, depends on this conserved angular momentum. Now, this equation, this expression, we solve for rho of t. Now, in the solution for rho of t, there will be another three parameters, namely the conserved energy E, the conserved angular momentum L, and an initial condition for rho. So rho at some initial time t0. Once we have rho as a function of t, for the complete solution we still need phi, the angular coordinate phi, as a function of t. In order to obtain phi as a function of t, we must insert the solution for rho of t that we had just obtained. We have to insert that solution into the area law. That gives us an equation for phi dot. This is this conserved angular momentum L divided by mu times rho squared, and rho is the solution that we had just obtained, rho of t. So this is the first order differential equation for phi of t, and the solution phi of t will contain one last integration constant in addition to all the others that we already have, namely the initial condition for phi, the value of phi at some initial time t0. So this is a complete list of all the integration constants that we encounter along the way. Let's add them up, and they are in total indeed 12, as we had expected. So we haven't lost any integration constants along the way.